All right, with that, the previous video talking about how a radical cation moiety can be delocalized and spread across an entire polymeric chain, leading to stability and therefore conductivity. Now let's move on to how does polyacetylene, how is polyacetylene formed from acetylene? Can we extrapolate the learnings so far, very basic learnings so far, to see how you can get polyacetylene from acetylene? Okay, let's try that. And let's see where it goes. Here we go. So here is acetylene, right? Right now I'm going to, now that you are a little bit proficient, I'm not going to draw too many hydrogen on this side, etc. That's acetylene, right? So how are you going to get polyacetylene? So this is acetylene, right? CH, CH, CH. So can we think of any way that we have known before? Just think of the first thing. Suppose it cleaves homolytically, right? Like this. All of them cleave homolytically, okay? What would the product be? CH dot, right? CH dot, CH dot. There's still a double bond, right? CH dot, CH dot, double bond, CH dot, CH dot, double bond, CH dot, right? Yada, yada, yada. So now you can see they can either come back, these dots, these radicals can come back this way, back here, to give you back the starting material, right? That's no reaction at all. That's just, looking at you, right? Or it can come between the next in empty space and the dot, the electron from the carbon of the next polyacetylene molecule can try to make a bond here with the two electrons. Similarly, this one can come here, this can come here, this can come here. Now you see what happens, right? CH, double bond, CH, then there's a bond, right? New bond, CH, double bond, CH, then new bond, CH, double bond, CH. That's your CHX, right? Just formed by radical chemistry. Correct? This is homolytic. This is all homolytic cleavage. Remember, I also was mentioning if you have CH, triple bond CH, CH, triple bond CH, 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 yada, yada, yada. I was saying you can also move arrows this way, right? Which will give you what? CH plus double bond CH minus, right? Correct? So this would be a CH plus double bond CH minus, CH plus double bond CH minus, CH plus double bond CH minus, correct? Now these are like magnets, right? These are two electrons here. Minus means two electrons, right? Formal charge. They just dive. Both these electrons can dive into this. There's no electrons here. That's plus, so it can form a bond right away, right? That's it. What do you get? CH plus double bond, CH bond, CH double bond, CH bond, CH double bond, CH bond, right? 2, 3, 4, 5, 6, right? Etc. Right? So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Right? That's gone this way. Okay, that's already gone. So let me put it this way. Yada yada yada. Right? It's amazing, right? I mean, you can get polyacetylene. formed by what? Ionic chemistry. Because it forms from ions, pluses and minuses, right? So there's two ways of doing this. So this is the second way, right? Is there another way? It's got to be just one or two, right? There can't be any other way. There's another way. Amazingly, right? You can switch this around, right? Suppose, yeah, let's talk about the third way in a minute, okay? So these are two major ways in which ionic and radical. There are two ways. Ionic is two ways. We'll come to that in a minute. But this is ionic way and a radical way to polyacetylene. So now coming down to what you have read, CH, triple bond CH, and a silicone oil. Now, what is that? 120 degrees, then to room temperature, and then Ziegler-Natta to give you undoped CHX, which when doped gives you very highly conducting polyacetylene, correct? So what the hell is all this? This has nothing to do, well, it does, right? It does have a lot to do with this. So generally acetylene will not give you polyacetylene. So what is the role of the Ziegler-Natta catalyst, right? So what it does, this is unreactive. The Ziegler-Natta, say let's call it zirconium, whatever, the cyclopentadienyl, the catalyst sucks the electron here, okay? Creating what? CH bond, zirconium, yada, 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 the catalyst, right? This is the catalyst. What's on this side? CH what? If the arrow has moved from here to here, you know the arrow formalism, right? If it lands over here, it becomes a minus, right? If it lands over here, it just makes a bond, right? New bond. That's the arrow formalism. If it's completely windshield wipers between two other atoms, it becomes a bond. There's no minus charge on this carbon. But there's a plus charge here, right? So cation. A cation is formed. Not cation anion. A cation is formed. Because this minus, which would have been formed, forms a bond with the zirconium catalyst. So this means it is activated. The acetylene gas gets activated, right? Now what can happen here? Remember, there's a lot of acetylene gas molecules nearby, right? The moment it sees this, these start windshield wipering automatically, forming bonds between each other to give you zirconium catalyst. I'm just going to put this, okay? The double bonds are on this side now, right? So yeah, zirconium, and that'll be this way. Keeps going, right? So this type of activation, which is activated by Ziegler-Natta catalyst, or titanium, right? Zirconium titanium, right? This is called cationic polymerization. Cationic polymerization, because the first species that's formed is a plus charge, which is the magnet that attracts the new acetylene molecules, and this becomes a zipper effect. So one starts, ta, 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 ta. The mechanism of Ziegler-Natta polymerization is very complicated. It's a graduate level organic class, but this is how it is. The fundamentals of this, it is a cationic, it's an electron sink that activates a acetylene molecule to give a plus charge in one end, which acts as a magnet for the others to follow suit. and connect with each other as like a pearl and necklace, right? So this is an important concept. So I'm going to stop here. So when you wanted to say, how do you draw the polymerization of acetylene? What is the role of Ziegler-Natta catalyst? And the role is to activate the acetylene molecule to give you a cation, and the cation acts as an electron sink. If it were to, on the other hand, a catalyst were to add electrons, then it will make the end of this chain negatively charged, and it will attack other acetylene molecules, pushing their electrons out on the other side, on the opposite side. Those polymerization reactions are called anionic polymerizations. So in ionic reaction, there are two types: cationic polymerization, anionic polymerization. And of course, we know the radical. We saw the radical already. That's the easy one that we saw first, simply a diradical. That's why I started this bonding lectures talking about radicals first, because it's easy to understand, then before going to ionics. Anyway, I'll stop here.